In today's video, let's learn the first principles derivation of Black-Scholes equation, a synthesis of stochastic calculus and no-arbitrage theory. The Black-Scholes model, a cornerstone of modern financial theory, provides a mathematical framework for pricing European-style options. Its derivation is not merely a mathematical exercise, but a profound thought experiment that constructs an idealized financial universe. To understand the model, one must first understand the control conditions of this theoretical laboratory, the set of assumptions that make the pricing problem mathematically tractable. These assumptions are not arbitrary idealizations, but a logically interconnected system designed to isolate the fundamental relationship between an option and its underlying asset. The Black-Scholes world is a theoretical construct where financial markets operate under a set of perfect and simplified conditions. This idealized environment allows for the application of powerful mathematical tools to derive a unique, preference-free price for a derivative security. By deliberately constructing this world, Fisher Black, Myron Scholes, and Robert Merton were able to transform the problem of option pricing from one of subjective forecasting into one of objective replication. First, let's look into the assumptions regarding market structure and dynamics. The architecture of the market in the Black-Scholes model is defined by the principles of efficiency and perfection. So the first assumption we make is there is no arbitrage in the market. This is the central economic pillar upon which the entire edifice rests. An arbitrage opportunity is defined as the ability to generate a risk-free profit with zero investment. The model presupposes a perfectly efficient market where such opportunities, should they ever arise, are instantaneously eliminated by actions of rational traders. The next assumption we make is that there is continuous trading in perfect liquidity. The model assumes that the underlying asset in the option can be traded continuously through time and in a very small quantity. Without continuous trading, risk could not perfectly be eliminated, leading to gaps in the hedge. The next assumption we make is that there are no transaction costs or taxes. All trades are assumed to be frictionless, meaning there are no commissions, fees, or taxes associated with buying or selling assets. If each trade incurred a cost, the total cost of maintaining the hedge over any finite period would be very large, making perfect replication economically unfeasible. The next assumption we make is that trades are placed in a perfect markets and there is short sell. The model assumes the existence of a single constant risk-free interest rate at which participants can both borrow and lend unlimited funds. Furthermore, it assumes that short selling the underlying stock is permitted without restriction and that the proceeds from a short sale are available for immediate use. The ability to short sell is not an incidental detail. It is mechanically essential for constructing the hedge. To hedge a long call option, one must hold a negative or a short position in the underlying stock. Now let's look into the assumptions regarding asset price behavior. The model makes specific assumptions about how asset prices evolve over time, choosing a mathematical representation that is both tractable and captures essential features of the financial assets. The first assumption we make is that the prices follow a log normal distribution. The model posits that stock prices follow a log normal distribution. This is a direct consequence of underlying random walk model used for asset returns, known as geometric Brownian motion. A critical feature of the log normal distribution is that it is bounded below by zero. This ensures that the stock price can never be negative, a realistic property that distinguishes it from the earlier models. The next assumption we make is that there is constant and known volatility. The volatility of the underlying assets returns is assumed to be known in constant value over the entire life of the option. Assuming constant volatility is what makes the resulting partial differential equation solvable in a closed form. Next assumption we make is that there is constant and known risk-free interest rate. The rate of return on a risk-free asset is assumed to be constant and known throughout the option's life. This simplifies the process of discounting future cash flows and calculating the deterministic growth of the risk-free component of the hedging portfolio. The next assumption we make regarding price behavior is that there are no dividends. The original Black-Scholes model assumes the underlying stock pays no dividends during the option's life. Dividends complicate the model because they cause predictable jumps downward in the stock price on the ex-dividend date, violating the assumption of a continuous price path. Now let's look into the assumptions the Black-Scholes world makes regarding the options contract. We assume there is only a European-style option. The model is specifically derived for European options, which can only be exercised at their expiry date. This constraint simplifies the valuation problem immensely by removing the need to consider the optimal strategy for early exercise, which is a key and complex feature in American options. Assumptions of Black-Scholes world form a self-reinforcing logical system. Now let's look into how we model the uncertainty of the Black-Scholes model. At the heart of a Black-Scholes model is the mathematical description of how an asset price evolves through the time under uncertainty. This description is built upon the concept of a random walk, which is formalized in a continuous time by value process. This process is then adapted to the model asset prices in a financially realistic way through a stochastic differential equation, or STE, known as the geometric Brownian motion. The foundation for modeling random movements in continuous time is the Bainey process, also known as the standard Brownian motion. It can be conceptualized as the limit of a simple discrete time random walk as a time step between moments approaches zero. A standard Bainey process is denoted by BT or WT, and it is characterized by three key properties. It starts at zero, that is, B naught of zero is equals to zero. It has independent increments for any two disjoint time intervals, S comma T and U comma V. The changes in the process B of T minus B of S and B of V minus B of U are independent random variables. The increments are normally distributed. That is, the change Bt minus Bs follows a normal distribution with a mean zero and a variance equal to the length of the time interval T minus S. While the binary process captures pure randomness, it is not a suitable model for stock prices on its own. Simple extension, the arithmetic Brownian motion with drift can be written as the ST of d of ST is equals to mu into dt plus sigma of dbt. Mu is the returns and sigma is the expected volatility and dbt is the randomness factor. However, this model suffers from a critical flaw. Since the random increments are normally distributed, this process can be negative, which is impossible for a stock price. To resolve this, the Black-Scholes model assumes that the asset prices follow geometric Brownian motion. This model is specifically engineered to process the properties required for realistic financial asset. The STE of GBM is T of ST is equals to U into ST into dt plus sigma into ST into dBT, where the term U into ST into dt is called a drift and sigma ST dBT is called a diffusion. The drift term is the deterministic component of a price change over an infinitesimal time interval dt. It represents the expected return of the asset, where U is the constant expected return of. The diffusion term is a stochastic or random component. The term dBT, as we discussed, represents the random shock from the underlying binary process. The magnitude of this random shock is scaled by two factors: the constant volatility parameter, which measures the standard deviation of returns, and the current stock price, ST. The proportionality to ST is a key feature of GBM. It ensures that the volatility of the return is constant and it prevents the stock price from becoming negative. One of the major reasons why GBM is widely used is that it has an analytical solution. Although formally deriving this solution requires Ito's lemma, the solution itself is given by ST is equals to S naught into exponential function of U minus sigma squared by 2 into T plus sigma of BT. Now taking ln on both sides to eliminate the exponential function, the equation transforms into ln of ST is equal to ln of S naught plus mu minus sigma squared by 2 into T plus sigma of BT. This is the solution for GBM using Ito's calculus. This is how the solution for GBM is derived. Discussing each and every step of this solution is very time consuming right now, so we'll look into it later. The non-differentiability of the Vanier process renders ordinary calculus insufficient for analyzing the functions of the stochastic processes. To address this, a new set of rules known as Ito's calculus was developed. The cornerstone of this framework is the Ito's lemma, which serves as the stochastic counterpart to the chain rule for deterministic calculus. In standard calculus, the chain rule allows us to find differential of a composite function. For a function f of x, where x is a function of time t, the change df is given by df is equals to derivative of function f of x into d of x. If we namely apply this to a function of a linear process fbt, we would write df is equals to derivative of function fbt into dbt. However, this is incorrect because it ignores a crucial feature of stochastic process, the non-zero quadratic variation. A Taylor series expansion reveals that second-order terms which vanish for deterministic functions make a non-negligible contribution in a stochastic setting. Ito's lemma can be derived heuristically by performing a Taylor series expansion of a function fst up to the second order, where st is a stochastic process following the geometric Brownian motion. The change of f over a small interval df is approximated as d partial derivative of f in terms of t into dt plus partial derivative of f in terms of s into ds plus half into second order partial derivative of f in terms of t into dt square plus half into second order partial derivative of f in terms of s into ds square plus second order partial derivative of f in terms of t then in terms of s into ds dt. We now substitute the st for st, which is d of st is equals to u into st into dt plus sigma into st into dbt. The key insight of Ito's calculus lies in how the squared differentials are treated in the limit as dt tends to 0. Based on the properties of the linear process, we have the following rules of thumb. dt squared tends to 0, dt into dbt tends to 0, and dbt squared tends to dt. The first two rules are intuitive. These higher order terms vanish faster than dt. The third rule is the heart of the matter, which while the expected value of dbt is 0, the variance while the expected value of dbt is 0, its variance is dt, which means that the magnitude of increment is of the order dt. Therefore, its square, dbt square, has magnitude of the order dt and does not vanish in the limit. Now, if we evaluate the term ds square, we'll get the simplification as this. Why? Because ds is equals to ust dt plus sigma st dt. Now, when we square these two, now when we square this equation, we get a term which is with a dt square and a term with a dbt square and a term with dt into dbt. So the term with the dt square and the term with dt into dbt tends to 0. So those terms are equated to 0. And the only term which is left is the term with the dbt square. And this term is simplified as sigma squared st square dt. Now, substituting all this back in Taylor's expansion, we get an equation as df is equals to partial derivative of f with respect to t into dt plus partial derivative of f with respect to s into u into st into dt plus sigma into st into dvt plus half of second order partial derivative of f with respect to s into ds squared. This is the simplified equation where the terms related to dt square and dt into dvt are equated to 0. If we evaluate this equation furthermore by putting up the value of ds square, we get this equation. For a convex function like call option, the gains from an upward price move are larger than the losses from a downward price move of the same magnitude. This asymmetry, a consequence of Jensen's inequality, means that volatility itself creates a positive drift in the options value. Even if the underlying stock has 0 expected change, the options value will tend to drift upwards simply due to the random fluctuations. Ito's lemma precisely quantifies this volatility-induced drift, providing a direct link between the abstract mathematics of stochastic calculus and practical financial concepts of an options gamma. Now, having established the mathematical framework for describing asset price movements and their functions, the derivation now turns to financial economics. The bridge between the stochastic world of asset prices and a deterministic valuation equation is built upon powerful principle of no-arbitrage, operationalized through a strategy of portfolio replication. We also discussed what a no arbitrage market is. It states that two assets or portfolios that have the same exact payoffs in all future states of the world must have the same price today. If they did not, a trader could simultaneously buy the cheaper asset and sell the more expensive one, looking in a guaranteed risk-free profit rate. Core idea of Black-Scholes derivation is to apply this law if the payoff of an option can be perfectly synthesized or replicated using a dynamic portfolio of the underlying stock and a risk-free asset. Then the price of the option must be equal to the cost of creating and maintaining the replication of the portfolio. This approach represents a paradigm shift. A name method for pricing an option might involve forecasting the future stock price, calculating the expected option payoff, and then discounting it back to the present. However, the correct discount rate for this calculation would depend on the risk preferences of the investors, leading to a subjective and non-unique price. The replication argument masterfully sidesteps this problem by constructing a perfect synthetic substitute for the option. The price is looked in by the no arbitrage principle. The valuation is no longer about subjective expectations of the future, but about the objective present day cost of engineering the replication portfolio. The mechanism for creating this synthetic option is a dynamic trading strategy known as delta hedging. A portfolio, let's call it pi, is constructed using two assets whose prices are known, the underlying stock S and a risk-free asset that grows at a constant rate R. The key to this strategy is to continuously adjust the holdings to the portfolio to offset the risk of the option. The change in the option's price for a small change in the stock's price is given by its first partial derivative with respect to the stock price, delta of S by delta of C. This quantity is known as delta. By holding an amount of stock equal to the options delta, a portfolio can be constructed that is for an infinitesimally small moment in time, immune to small changes in stock's price. The central argument is that by continuously rebalancing the portfolio, that is, adjusting the number of shares held to always match the option's current delta, one can construct a portfolio whose change in value over any infinitesimal time step, dt, is completely deterministic. All the random shocks from the stock's movement are precisely cancelled by the corresponding changes in the option value. Once such a risk-free portfolio is constructed, the no arbitrage principle provides an unambiguous statement about its return. It must earn exactly the risk-free rate of interest R. If the portfolio earned more than R, an arbitrager could borrow at R, construct the portfolio, and earn a riskless profit. If it earned less, one could short the portfolio and invest the proceedings at R for a similar riskless gain. Therefore, the change in the portfolio's value, d pi, must be equal to R pi dt. D pi must be equal to R pi dt. Now, this section brings together mathematical machinery of stochastic calculus and the economic logic of no arbitrage to derive the celebrated Black-Scholes partial differential equation. First, we define a replication of a delta hedging portfolio, where portfolio value is equals to minus C plus delta S. Then we construct a function of the underlying stock S at a time t, which is similar to the call option price, since the call option price is taken as a function of the stock S at time t. Now, from the previous derived equation of f of st, we can say that d of c is equals to partial derivative of c with respect to t plus u into st into partial derivative of c with respect to s plus half into sigma square into st square into second order partial derivative of c with respect to s whole into dt plus sigma into st into partial derivative of c with respect to s into dbt. Since a portfolio is equals to minus c plus delta s, where the portfolio contains 1 unit of shorting of derivative and a long position in sigma units of the underlying stock, the change in portfolio can be written as d pi is equals to minus d c in plus delta into ds, or partial derivative of c with respect to s into ds. Now, if we plug in the values of dc and ds into this equation, we get d pi is equals to whole minus of partial derivative of c with respect to t plus u into st into partial derivative of c with respect to s plus half into sigma square into st square into second order partial derivative of c with respect to s into dt minus sigma into st into partial derivative of c with respect to s into dvt plus partial derivative of c with respect to s into u into st dt plus partial derivative of c with respect to s into sigma dvt. Now, if we cancel out the common terms, which are this, and this, we get the simplified equation as d pi is equals to minus of partial derivative of c with respect to t minus 1 by 2 into sigma square into st square into second order partial derivative of c with respect to s into dt. As previously established, this instantaneously risk-free portfolio must earn exactly the risk-free rate of return R. Any other return would create an arbitrage opportunity. Therefore, the change in the portfolio's value must be given by d pi is equals to r pi into dt. Now we substitute the values of d pi and pi into this equation. Then we get a whole minus of partial derivative of c with respect to t plus half into sigma square into st square into second order partial derivative of c with respect to s whole into dt is equals to r into minus c plus partial derivative of c with respect to s into st dt. Now, after simplifying this expression, we get the final Black-Scholes PDE, which is equal to partial derivative of c with respect to t plus r into st into partial derivative of c with respect to s plus half into sigma square into st square into a second order partial derivative of c with respect to s square minus rc is equals to 0. The Black-Scholes PDE is more than a mathematical result. It is a profound statement about the nature of derivative pricing. By analyzing its structure, we can gain deep insights into the financial principles it embodies and its practical implementations of risk management. The PDE establishes a precise dynamic relationship between the value of an option and the variables that determine it. Each partial derivative in the equation corresponds to one of the creeks, which are standard measures of risk used by traders and portfolio managers. The partial derivative of C with respect to T is called theta, representing the rate of decay of options value with the passage of time. The partial derivative C with respect to S is called delta, which is the rate of change of options price with respect to the underlying stock's price. The second order partial derivative of C with respect to S is called gamma, which is the rate of change of delta with respect to the stock's price, measuring the options convexity. This form provides a direct link between the abstract differential equation and the practical realities of managing an options portfolio. Perhaps the most striking and revolutionary feature of Black-Scholes PDE is the absence of the parameter U, the expected rate of return of the underlying asset. This is a direct mathematical consequence of delta hedging and replication argument. The terms involving U are cancelled out precisely because the portfolio was constructed to eliminate all sources of uncertainty related to the stock price's movement. The implication of this is profound. The price of a derivative does not depend on the expected return of the asset on which it is written. Two investors with widely different expectations for the stock's future performance, one believing it will soar and the other that it will stagnate, must still agree on the same price for an option on the stock. This is because the option's value is determined not by the expected future price, but by the cost of perfectly replicating its payoff using the stock and a risk-free bond. The derivation of the Black-Scholes equation represents a landmark achievement in the financial economics. It is an elegant synthesis of a powerful economic principle called the no-arbitrage and the sophisticated mathematical tools of stochastic calculus. The model provided for the first time a rational and objective method for pricing options, transforming them from speculative instruments into manageable tools for risk transfer. Thank you.